Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had completed or we were discussing multi-carrier modulation, and we said that after modulating the transmission symbols on multiple subcarriers and transmitting this composite signal through the communication channel, we said that each subcarrier or the data symbol on each subcarrier can be coherently demodulated by employing the subcarrier E j 2 pi L B over N T. That is, I am demodulating the symbol that is transmitted on the Lth subcarrier using coherent demodulation or demodulation using the Lth subcarrier. Okay. Further, we said that multi-carrier modulation is transmitting n times n information symbols in parallel over a time period of n over b. Remember, the time period also increased to n over b, hence the net it transmits n symbols in n over b, which essentially means it is transmitting one information symbol in time period 1 over b, giving it a data rate of b symbols per second, which essentially is the same as that of a single carrier system. That is what we said last time. We also looked at the schematic of this multi-carrier system modulation system, that is a schematic at the transmitter, and we also looked at the schematic of the receiver or the architecture schematic of the receiver. Further, we also said, since both the multi-carrier modulation system and the single carrier system are transmitting symbols at the rate of b, the advantage of a multi-carrier system is essentially by dividing this wide band into multiple subcarriers of narrow band, we are ensuring that this system is not subject to intersymbol interference, because the bandwidth of each subcarrier is much less than coherence band. Thus, by ensuring that the bandwidth of the subcarrier is much less than the coherence bandwidth, we are essentially removing the effect of intersymbol interference, which is a greatly simplified receiver design in wireless, especially broadband wireless communication systems. And further, we also saw that there is one problem with multi-carrier modulation, which is essentially that it requires n modulators over the subcarriers and n demodulators, which was essentially solved by an ingenious idea by Weinstein and Ebert, who proposed a novel transmission scheme which we were discussing, which is related to considering the FFT. So, what we said was, we consider, since the signal is band limited to B, instead of transmitting the signal directly, we will sample it at the Nyquist rate, that is corresponding to B samples per second, which means sampling rate of 1 over sampling time interval of 1 over B, and consider the sampled signal, and we saw that that sampled signal can be generated by nothing but the IFFT, or the IDFT of the transmission symbol. So, today let me illustrate that idea further. So, we considered a signal ST. This is, remember, the MCM transmission signal, MCM composite transmit signal. This is given as, we said, xi e to the power of j 2 pi I b over n t. This is the information symbol, the ith stream, and this is the ith sub carrier. What I can do is, I can sample this at rate b, which means sample time Ts equals, or sample interval Ts equals 1 over b. Let me consider the uth sample. Uth sample, or the time corresponding to the uth sample, is nothing but uts, which is u over b. This we say is the time instant of the uth sample. All right, this we say is the time instant of the uth sample. That uth sample x of u is nothing but s of u Ts, which is equal to s of u over b, that is nothing but summation over I xi e to the power of j 2 pi I b by n over t, but t is nothing but u by b. This you can clearly see is summation over I xi e power j 2 pi I u over n, and this is nothing but this is the IDFT. This is the IDFT of the transmission and this is a very important result because it says I do not need these n modulators to generate the composite signal. I can generate a sampled version of that signal, sampled at rate b, which is the Nyquist rate, by essentially computing the IDFT, and there is a very fast algorithm to compute the IDFT, which is simply the IFFT, or the inverse fast Fourier transform of the symbols. Hence, one can compute the IDFT. Let me just simply write here what IDFT stands for. IDFT equals the inverse discrete Fourier transform, and in practice IDFT is computed using IFFT, which is essentially the inverse fast Fourier, which is essentially a fast algorithm to compute the inverse fast the IDFT, or the inverse discrete Fourier transform. All right. So, in practice what it means essentially is that from the structure given here, I can take my transmission signal symbols to be transmitted, that is the x0, x1 up to x capital X of n minus 1, and compute a simple IDFT of these symbols, or the IFFT of these symbols, to generate the transmit signal, and there is no need to use the n modulators for the n subcarriers, which greatly which as we saw, employing n modulators greatly increases the complexity of this system. So, this scheme so this scheme, that is to generate the signal by computing the IFFT instead of the n modulators, were proposed by Weinstein and Ebert. This was the scheme that was proposed by Weinstein and Ebert in their 1971 paper. So, this scheme of generating the composite transmit signal employing IDFT was proposed by Weinstein and Ebert in 1971. In fact, we also talked about the paper in which this novel scheme was proposed in. In the last lecture, I mentioned a reference of a paper in which this novel scheme to generate the multicarrier modulated signal was proposed by Weinstein and Ebert. What it says is, instead of using n modulators, the composite MCM transmit signal can simply be generated by an IFFT operation. So, the composite MCM transmit signal can simply be generated by employing an IFFT, and this is the key, an IFFT operation, which means there is no need to use the n modulators, one for each subcarrier, and that greatly simplifies transmitter design. And this scheme was of course proposed, and this scheme, this proposed scheme of generating the transmit signal by using IFFT has much lower computational complexity than using, much lower implementational complexity than using the n modulators, or which is the bank of modulators of generating the MCM transmit signal has much lower implementation complexity compared to using the bank of this. So, this has much lower complexity compared to using the bank of modulators, thus significantly enhancing the appeal of this system and significantly enhancing the realizability, the practical realizability of this system based on multi-carrier modulation. And this system, multi-carrier modulation with the signal transmission replaced by IDFT, this has a name, this is known as OFDM. Alright. So, this MCM with signal generation done by the IFFT operation is termed as OFDM. So, this is termed as OFDM, which as we said is the key technology for next generation wireless communications, 4G such as LTE, WiMAX and WLAN, and it stands for orthogonal frequency division multiplexing, and this stands for orthogonal frequency division multiplexing. And I said this is essentially multi-carrier modulation with the signal transmission, signal generation replaced by the IDFT, or in practice the IFFT operation, which is the fast operation implemented on a DSP chip in a modern wireless communication system. All right. And now what can be done at the receiver? Receiver, instead of using the bank of demodulators, I can simply use the inverse of the IFFT operation, which is the FFT operation. So, at the receiver now, to recover the information symbols, one can correspondingly employ an FFT . All right. So, instead of the bank of demodulators at the receiver, now you can do an FFT to recover the transmitted symbol. So, at the transmitter, the bank of modulators is replaced by an IFFT. At the receiver, the bank of demodulators is replaced by an FFT. That greatly simplifies transceiver design in wireless communications, and that is essentially the genius contribution of Weinstein and Ebert towards realizing this multi-carrier modulation system. And now you can get all the gains of the multi-carrier modulated system, the advantages, which is essentially removing the effect of inter-symbol interference, as we are going to show next. So, before we proceed further, let me give you a simple schematic of this multi-carrier modulation system, similar to of the OFDM system, similar to the multi-carrier modulation system. So what I am going to do here is similar to what we have done earlier. I am going to draw the transmitter and receiver schematic, that is the architecture of the transmitter and receiver, and to illustrate how the transmission and detection of symbols is done. Okay. So we have, so let us say we have the schematic of OFDM. I have a similar to what I had in a multi-carrier system. I have the serial to parallel demultiplexing. This is a demultiplexing operation. Remember, I have a serial stream. I have to convert it into parallel to modulate it over the n subcarrier. So I am basically converted into a parallel block for modulation, except now I am no longer going to use the bank of modulators. I am going to use the simple IFFT operation. So now I am going to simply use, instead of a bank of modulators, I am simply going to use an IFFT of size n, where n equals number of subcarriers. Okay. So the symbols x0 to xn minus 1 are going into the IFFT. That is, what is going into the IFFT are the actual constellation symbols. These are the constellation symbols such as BPSK, QPSK, the digital symbols. What comes out of the IFFT are the samples which are to be transmitted and which correspond to the signal. So I get the samples to be transmitted, and now I do the inverse operation, that is convert this parallel to serial, or I multiplex them for, so to convert it into a stream which can be transmitted over the channel, I convert the parallel to a serial stream. This can now be transmitted. This is for transmission over the channel. This signal can then be transmitted over the channel. So this is x0, x1 up to xn minus 1. This is transmitted over the channel. So let me write this over here. Remember, these are samples at sample rate, hence each sample occupies an interval of t sample, which is essentially 1 over b. So samples at rate b, that is samples are transmitted at rate b, that is b samples per second, or essentially what we also say is the sample time or the sample interval is 1 over b. So this corresponds to samples transmitted at rate b corresponds to sample interval of 1 over b. Now this is the transmitter schematic. How does the corresponding receiver schematic look? So at the receiver, once I receive the information from the channel, so I am receiving the serial stream from the channel. I compute, I first perform, again similarly I perform the serial to parallel demux operation, that is I demux this, because remember I have to pass this to the FFT block. So I demux this and then I pass this to the FFT block. this block performs the inverse of the IFFT. If remember, FFT is the inverse of the IFFT, and hence this helps recover or detect symbols at the receiver. This is to detect symbol on each sub carrier, and remember this replaces the bank of demodulators, that is the coherent demodulation with every sub carrier that we had illustrated earlier. This replaces the bank of demodulators in a multi-carrier modulated system. Once I do this, once I finish with this, what remains then is to take these parallel information symbols and convert them back into a serial stream so that they can be forwarded to the higher layers to the necessary application. So, this is again a parallel to serial or parallel to serial or multiplexing operation to applications. Alright, so the parallel serial, this again converts the parallel block into a serial stream, at which point I have my x0, x1, xn minus 1 which are passed on. Alright, and this is an OFDM receiver schematic. This is the receiver schematic. Okay, so this is the current receiver schematic that we have. Okay. So, what is the novel technique that has been proposed in the context of multi MCM? The novel technique is essentially to replace the generation using bank of modulators by an IFFT, which greatly enhances the practical realizability of that system. In fact, it drastically enhances the practical realizability, because implementing an IFFT is much more simpler than implementing a bank of modulators corresponding to each sub carrier. That is the great idea which has helped make OFDM possible. There is one more small modification to OFDM, because OFDM is in its current form that we have proposed is not yet usable because of the problem of inter-symbol interference that exists in the wireless channel. So, the next modification, which essentially is the slight modification to this scheme, is what we are going to talk about next. This is termed as the cyclic prefix or the cyclic prefix. This is termed as the cyclic prefix in an OFDM system. What does this essentially mean? Let us see what we have looked at before. Let us consider the system so far. I have an OFDM system that is, as we have seen, serial to parallel. This is the incoming information symbol stream. I have something that converts from serial to parallel. I have converted it into parallel. Then I employ my IFFT operation, at which I have a parallel IFFT. Then I convert this back into a serial stream. This is, as we said, a multiplexing operation, at which point I have the samples that I am going to transmit. This in fact is known as one OFDM symbol. This group of x0, x1, xn minus 1, small x0, x1, xn minus 1, which corresponds to the samples of capital X0, x1, xn minus 1, which are the block of n information symbols, is known as one OFDM symbol. Okay. So, I have one OFDM symbol which essentially consists of this is termed as an OFDM symbol. This essentially corresponds to This corresponds to FFT of x0, x1 up to x of n minus 1. So, I take a block of capital N symbols 0 to n minus 1, compute their FFT or compute their IFFT, I am sorry, this corresponds to the IFFT, and then transmit these samples. These samples collectively form one OFDM symbol. So, we transmit one OFDM symbol after one OFDM symbol after one OFDM symbol. So, now we have one OFDM, each OFDM symbol comprising of n samples transmitted successively. Okay, so that is the transmission scheme that we have so far. So, at this point I have the data symbols, and at this point I have the IFFT samples. Okay. So, I have the IFFT samples. These are transmitted, of course, as we said, these are transmitted at rate B or time interval 1 by B. So, I will say these are transmitted at rate B. Okay. So, now let me go to illustrate what happens during one such transmission. Let us say I am considering one symbol x0, x1, x2 up to xn minus 1. These are the samples corresponding to one OFDM symbol, and let us say the previous OFDM symbol also has some samples. These samples are x tilde n minus 1, x tilde n minus 2, x tilde of 0. So, these are the previous OFDM symbol. This is a current OFDM symbol. So, I have a block of n samples corresponding to the current OFDM symbol. I have a block of n samples corresponding to the previous OFDM symbol. Now, what we want to do is we want to consider a frequency selective channel similar to what we have seen earlier. So, now remember we considered a frequency selective channel in the context of CDMA also, where we illustrated the performance with respect to rake receiver and so on. In there we said that the frequency selective CDMA system, it can be modeled as a frequency selective channel can be modeled as a multipath channel. It can be modeled similar to a FIR digital filter. So, I will choose the taps of this multipath frequency selective channel as follows. The frequency selective channel can be modeled as a multi-tap channel with taps H0, H1 up to HL minus 1. So, just to remind you again, this is a multi-tap channel and it has 0 to L minus 1, that is L taps. All right. We said this is the model of a frequency selective channel. I am transmitting my OFDM symbol block across this frequency selective channel, and I want to see what kind of a signal is arriving at the receiver and is there any problem with the signal that is arriving at the receiver. So, now I pass this two OFDM symbols, in fact big OFDM symbols of duration n over b through this multipath channel. Let us look at the first symbol that is received. So, the first symbol corresponding to the current OFDM block, OFDM symbol block, the first The first symbol is y0 equals h0 x0, that is h0 times the first sample. But this is not the only component that is present. There is, remember, this is a multipath frequency selective channel, which means there is intersymbol interference. There is h1 times x tilde n minus 1. Remember, the previous sample corresponding to x0 is x tilde n minus 1. Hence, I will have an x tilde n minus 1 plus h2 x tilde n minus 2 plus h L minus 1 x n minus L plus 1. In fact, corresponding to the current sample x0 or sample x0 in the current symbol, there is interference from L minus 1 past sample. So, this actually, this whole component here, that is in the circle area, this is from the previous OFDM symbol. So, this is x tilde, this is from So, what we have done is we have increased this OFDM symbol size, that is what we had earlier. We had a transmission time of 1 over b. Now, we increase the transmission time to 1 over to n over b. So, now we have an increased OFDM symbol size. This is transmission time n over b. This is increased OFDM symbol size. Increased symbol size corresponding to transmission time n over b. That is, I am making this symbol essentially look like something with a symbol time that is much larger than the delay spread of the channel. Remember, that is the essential idea behind intersymbol interference. If the delay spread is much smaller than the symbol time, or the symbol time is much larger than the delay spread, then the intersymbol interference can be neglected. However, now there is intersymbol interference, however small it is in the initial part of the period. So, the initial samples in this OFDM symbols are being subject to intersymbol interference. So, initial samples are being subject to the initial samples in this system are being subject to intersymbol interference. So, and in fact, let us continue with that example. Let me also illustrate what is happening with the second received symbol, that is y1, just to cement this idea. When I receive y1 is nothing but, now you can also see it is h0 x1 plus h1 x0. Until here it is fine, this is the same OFDM symbol, but now when you look at h2, I have h2 x tilde 0 plus so on h L minus 1 x tilde n minus L n minus L plus 2, all right, and this portion here again corresponds to the intersymbol interference part. Okay. So, this portion here, if you look at this portion here, again corresponds to the intersymbol interference ISI from previous. Remember, not the previous symbol as in the case of narrowband system, this is from the previous OFDM symbol. There is a big difference because this OFDM symbol is much larger, it consists of n samples. So, there is the effect has been decreased by increasing this OFDM symbol size. However, there is still this effect of intersymbol interference in the initial part. Alright. So, OFDM as it stands now still suffers from that intersymbol interference part for the initial part of this large symbol. So, what is the solution to overcome this problem? We consider a simple transmission scheme in which what we are going to do is we are going to take the transmitted samples x0, x1, xn minus 1. Now, instead of transmitting this directly, what we are going to do is we are going to take a small portion of this. We are going to take a portion of this comprising of some symbols, and we are going to repeat that portion here as follows. I am going to prefix this with xn minus 1, xn minus 2, xn minus L plus 1. Okay. So, this is essentially a prefix. Let me name this. First, this is a prefix, and there is a cycle here, that is whatever I have here is cycled back to the end, hence this is known as cyclic. This is known as cyclic prefix. Alright, cyclic prefix is nothing but I take the OFDM sample, OFDM symbol, that is I take some samples of the OFDM symbol, move and back and prefix the OFDM samples of the OFDM symbol with these samples which are towards the end. This is a cyclic, this is cyclic in nature, it is a prefix, this is known as a cyclic prefix. That is what we are going to consider now, which is the cyclic or the cyclic prefix for OFDM. What is the advantage of the cyclic prefix for the OFDM? How does the transmission of the cyclic prefix affect this procedure of OFDM? That is what we are going to look now. The received symbol y1 in this scenario is given as follows. Now, let us look at y1. y1 across the same inter-symbols interference ISI channel, multi-tap ISI channel which taps H0, H1, HL minus 1 is given as H0, or sorry, let us look at y0. y0 is given as H0 x0 plus now H1 into, look at this, the previous symbol to x0 is nothing but xn minus 1. So, this is H1 into xn minus 1 plus Hn minus 1 into xn minus L plus 1. So, now because we are not directly transmitting the two OFDM symbols next to each other, instead we are cyclically taking some of the last samples of this OFDM symbols and prefixing these samples to the current OFDM symbol. I have removed the impact of intersymbol interference on this OFDM symbol. Alright, so now you can look at this part, all the symbols belong to the, say, all the samples y0 belong, all the samples belong to the same OFDM, belong to the current OFDM symbol. So, all samples belong to current OFDM symbol. Hence, this is, now you can similarly look at y1. Let me also write y1. y1 equals h0 x1 plus h1 x0 plus hn minus 1 xn minus L plus 2, so on so forth. In fact, you can look at the n minus 1 symbol, which is h0 xn n minus 1 plus h1 x n minus 2 plus so on and so forth. Hence, I have removed the effect of intersymbol interference. Okay, that is the first thing I want you to observe. In fact, I can write this as h l minus 1 x n minus l. Okay, I can write this as h l minus 1 x n minus l. Okay, so now you can see essentially that what I have done here is essentially I have removed by prefixing this OFDM transmitted symbol, this large symbol of samples x0, x1, xn minus 1. With this samples, I have removed the effect of intersymbol interference. In other words, nowhere is the intersymbol interference arising from samples of the previous OFDM symbol, which was remember the symbol x tilde n minus 1, x tilde n minus 2. By prefixing this, now I have restricted the intersymbol interference to the same OFDM symbol. And more importantly, observe, look at the nature of the convolution that we have right now. Remember, I am transmitting sequence of symbols to this LTI system, hence the output is the convolution of this transmitted samples with the channel filter. But look at the nature of the convolution. It is y0 equals h0 x0 plus h1 xn minus 1. It is as if I am wrapping this x0 xn minus 1 around this filter, and most electrical engineering students will be familiar with this type of a convolution. This is not a linear convolution anymore. In fact, this is a circular convolution. So, this convolution, which has a very unique nature, this is in fact a circular convolution, because look at this. It is like I am taking the filter and h0 I have at x0, but h1 I have at xn minus 1, h2 I have at xn minus 2 and so on, and progressively I am taking this filter and circularly shifting it over the transmit sequence. Hence, this is nothing but a circular convolution. So, what this is this has an interesting structure. This has a circular, this is a circular convolution. So, this is a circular convolution, which means now my output of samples, received samples y0, y1, yn minus 1 is nothing but the channel filter h0, h1, hl minus 1, appropriately 0 padded because they have to be same length, circularly convolved with x0, x1, xn minus 1. These are the received samples. Okay, y0, y1, yn minus 1 are the received samples. This is the multi-tap channel filter, or this is the ISI channel, or this is the multi-tap channel, which is a model of the intersymbol, which models the intersymbol interference channel. This models the intersymbol interference channel, and this x0, x1 up to xn minus 1, this is nothing but these are the n samples of the transmitted OFDM signals generated after the IFFT operation. Remember, we are still performing the IFFT operation. These are the n samples of the current OFDM symbol of the So, these are the n samples of the current OFDM symbol block, alright, which are generated by the IFFT of the transmitted modulated symbols, which is capital X0, capital X1, capital Xn minus 1. Let me remind you of that. So, now I can write this y equals h circular convolution with h, and this is possible because of addition of this this is possible because of the addition of the cyclic prefix, and that is the key. This is possible because of the addition of the cyclic prefix, which is the essential key, that is the key. And now once I have this, we all well know as electrical engineering students that if y is the circular convolution of x, h and x, I can write the DFT of y, capital Y, as h times DFT of x, or instant, or what I mean is yk, which is across the kth frequency in the IDFT, in the DFT equals h, or in the DFT. So, if I take the DFT of y, that is nothing but yk equals hk times xk. This is the main result that we want to show. Let me again define each of the terms in this. Yk, this is nothing but, in fact, let me make it additionally clear, this is the endpoint DFT of y. This is the endpoint DFT of h after 0 padding. Of course, that is assumed, that is implicit. Let me write that also clear, because after 0 padding, because it has only h0 up to hl minus 1, after 0 padding, and xk is nothing but the DFT of the transmitted OFDM samples, but the transmitted OFDM samples are themselves the IFFT or the IDFT of the capital X's, x0, x1 up to xn minus 1. Hence, DFT of IFFT gives me the same original transmitted symbols. So, these are nothing but the modulated and by modulation I mean a digital modulator, that is by PSK, QPSK or QAM modulated information symbols. What we are saying is, by performing an endpoint DFT, because by the addition of the cyclic prefix this has been converted into a circular convolution, I can perform an endpoint DFT, and what I have is each symbol xk is multiplied by hk, which is now the channel coefficient corresponding to that subcarrier, and that is received at the kth DFT point of the output received samples y0 up to yn minus 1. And now if you see, and so this is the symbol transmitted on the kth subcarrier. This k corresponds to what? This k is nothing but the kth subcarrier. This k is nothing but the kth frequency point of the DFT. This is nothing but the kth subcarrier, and what we are saying is the symbol transmitted on the kth subcarrier is essentially hk, the coefficient of the kth subcarrier, and that is the received symbol. So, we have yk equals hk into xk on the kth subcarrier, and this we say is nothing but a flat fading channel. Why is this a flat fading channel? Look at this, is the symbol on the kth carrier, this is the channel coefficient. So output, so we write output equals channel coefficient times symbol. So I have nothing but the symbol, and this is at the kth subcarrier, and this is, remember, at every subcarrier. So this is the kth subcarrier, and the output at the kth subcarrier is nothing but the symbol transmitted on the kth subcarrier times the channel coefficient. Hence what we have is, we have removed the effect of inter-symbol interference across this subcarrier. Alright, because if you look at this, that is what our main motivation was for using MCM or OFDM, that is to convert this wideband channel, which is a frequency selective channel, into a flat fading channel by removing the effect of inter-symbol interference, and this precisely illustrates that effect, where symbol xk into channel coefficient hk equals yk, that is nothing but, this is nothing but a flat fading channel. So let me again clarify that this is a flat fading channel across the kth subcarrier. Okay. Hence the OFDM symbol, OFDM, hence addition of the cyclic prefix, this is the complete OFDM system. Hence OFDM effectively converts a wideband frequency selective channel into a collection of parallel narrow band flat fading channels, thus removes the effect of inter-symbol interference, and because it uses the simple IFFT FFT based design, it is also very low in implementation complexity. Hence what we have here is, hence the frequency selective channel is converted into a group, remember we have now n narrow band flat fading channels across each subcarrier. It is converted into a group of narrow band flat fading channels, one channel across each subcarrier. It is converted into, hence the frequency selective channel is converted into a group of narrow band flat fading channels with one subcarrier, one channel across each subcarrier. That is the big advantage of OFDM. For instance, what you can clearly see what the advantage of OFDM is. For instance, consider that we used a single carrier system. Let's go back to our single carrier system. If you use a single carrier system, then what we have is x0, x1, xn minus 1 and so on. These are the actual symbols. There is no IFFT, FFT operation involved. Hence, these samples are nothing but the actual symbols. These are the samples. These are also actual modulated symbols in a single carrier system. Now, if I look at the reception at the receiver, that is y0 equals h0 x0 plus h1 x of, or let me write this, or let's look at it at symbol n, xn plus hn x minus 1 plus hl minus 1 x n minus l plus 1, and you can see all these symbols experience inter-symbol interference, and there is heavy inter-symbol interference. All right. So, single carrier system, there is heavy So, the greatest advantage of OFDM is that it has very low implementation complexity, and plus it converts a frequency selective channel into multiple parallel flat fading channels, and removes the effect of inter-symbol interference, thereby greatly enhancing the practical implementation, the realizability of such systems, and paving the way for realizing broadband wireless communication systems in 4G wireless communication systems in next generation wireless networks. So, with this we will conclude the lecture today, and we will discuss other properties of OFDM starting from this point in the next lecture. Thank you.